Hey guys, we are going to start today with section 1.1, linear equations. This is for college algebra. Linear equations, when we say that, what we mean is equations in one variable. They are first degree. I have a spelling error. Hopefully I remember to fix it before I run your copies, so yours might be spelled correctly. First degree, which means that the highest power on the variable is 1. Okay, now equations can be true, such as if I say x equals 4, that's a true equation, except it's only true when x is 4. Like if x was any number other than 4, like 7, I would have the equation 7 equals 4. So we call this a conditional equation, and that means that there is one solution. But sometimes we end up with other stuff, like at the end, we end up with x equals x, or 2 equals 2, or 7 equals 7. That is what we call an identity. And identities have an infinite number of solutions because they are always true. So in both of these cases, those equations are true. But what would happen if we had something like 8 equals -7? That is never going to be true. We call that a contradiction. That means there is no solution, or sometimes instead of writing out no solution, we can use the symbol like that represents empty set. So are equations always true? No. When we are solving equations, just a few reminders of legal things that we can do. You can add or subtract the same thing to both sides of the equation. And that could be a number, it could be a variable. As long as we add and subtract the same thing on both sides of the equation, we are good to go. We can multiply and divide both sides of the equation by the same expression. However, we have to be careful to avoid one thing. So we can multiply or divide both sides by the same, I'm going to leave a blank here, by the same expression. But we have to avoid multiplying and dividing both sides by 0 because that causes us problems, as we'll see throughout this course. So I'm going to say multiply or divide both sides by the same non-zero expression. And then we're allowed to simplify both sides. Now, when we say simplify, I mean, you hear that a lot in math. You hear it with fractions, you hear it with regular numbers, you hear it all over the place. So I'm going to be a little bit more specific. When we're simplifying both sides, we might be distributing. We might need to factor, but then again, we might need to FOIL. And we might need to combine like terms. And then the other legal move in solving equations is switching sides. So you can switch sides. That's exclusive to equations, really. If you have an inequality, you can switch sides, but there's a little bit more to it, and we'll get to that in another section. So let's practice on solving some equations here. This first equation, when you look at it, I know that fractions are not our favorite thing, so I'm going to teach you a strategy that you can use moving forward to deal with equations and other critters when you have fractions. So what we're going to do is we are going to clear the fractions. I'm going to put that in quotes because that's really not a legitimate math term. It's just how I describe it. And the way that you're going to clear the fractions is by multiplying each term by the LCD over 1. You're going to see this strategy over and over again all semester. So it's a good one to keep in the back of your mind and be able to come back to and pick up later. So I'm thinking about the LCD of my fractions. I have 1/3, so that denominator is 3. The number 2 actually has a denominator. It's just not written. It's 2 over 1. And then 3/2, of course, has a denominator of 2. So the LCD is going to be 6. So what I want to do is multiply each term by 6 over 1. So I'm going to do times 6 over 1 times 6 over 1 times 6 over 1. And then I'm thinking to myself as I do this, how do I do 6 over 1 times 1 over 3? So here's my little remembering bubble. To do 6 over 1 times 1 over 3, when we multiply fractions, we just go straight across. So I'll do 6 times 1, which is 6, 1 times 3, which is 3. So 6 over 1 times 1 over 3 is going to be 6/3, which I will, of course, simplify to be 2. So this becomes 2x equals, I'm going to do the same thing here. 6 times 2 is 12. 1 times 1 is 1. That becomes simply 12. Make sure you pay attention to signs as you go. So that's minus. And then again, thinking back to doing 6 over 1 times 3 over 2, which is going to give me 18 over 2. That simplifies to 9. Don't forget your x that's attached. So 2x equals 12 minus 9x. Then this problem is a lot more simple to work with. So I am going to go ahead and add my 9x to both sides, which is going to now give me 11x equals 12. And then we divide both sides by 11. And it's an automatic fraction. So the left side is going to leave me with x. The right side is my answer. It's 12/11. Fractions are perfectly acceptable answers. I would rather you not make those into decimal approximations. Just use 12/11 as your answer, unless the little blue words in my math lab say like round to a certain amount, then you can use a calculator to get a decimal. Turn the page. Equations sometimes lead us to linear equations. So this equation right here looks really disgusting, but it's going to end up giving us a linear equation when it's all said and done. So let me show you how that happens. First of all, we're going to clear our fractions, but before we do that, we want to factor this guy here, this x squared minus 9. Hopefully that is familiar to you from your time in your previous math classes. It is difference of squares, which I will always abbreviate DOS. So difference of squares, remember, goes first squared minus last squared, factors into first plus last times first minus last. If you need a refresher on factoring, let me know so that we can get that done, because it is going to be important that you know how to factor going forward the rest of the semester. So when I factor this, I will have x over x plus 3 times x minus 3 plus, I'm going to leave some space here because I know what I'm going to be doing here, 4 over x plus 3 equals 3 over x plus 3 x minus 3. Maybe I'll write that down again later. We'll see. Okay. The next thing we need to do is we need to look at domain restrictions. Now, domain restrictions is also a persistent topic. Throughout the course, you're going to need to automatically, without even hesitating, be able to find domain restrictions. It's like, we'll talk about it a lot. So domain restrictions in this instance mean that we need to avoid where the denominator would equal 0. So we have a restriction whenever we have variables in the denominator. We'll see a couple of other instances for domain restrictions coming up before you know it. So when there are variables in the denominator, your strategy is going to be that we set the denominator either equal to or not equal to 0, whatever your preference is. And that's going to identify the restrictions. So those are going to be the things that we need to avoid. So in this particular instance, we have 3 little denominator dudes. So if I set x plus 3 times x minus 3 cannot equal 0, then from your time in Algebra 2, we know that that means that either x plus 3 cannot equal 0 or x minus 3 cannot equal 0, which means x cannot equal negative 3, x cannot equal 3. Then we would go on to the next thing, and I see x plus 3 cannot equal 0. Well, that's a rerun of what we already had over here, and this one is also a rerun of what we had over here. So our 2 restrictions are that x cannot equal 3 and x cannot equal negative 3. There are different ways that you can list your domain restrictions. One of those ways is called set builder notation. And it seems to be a favorite of my math lab. So we'll just talk about it here. Set builder notation, you have the squiggly brace, and then the letter, whatever your variable is, our variable is x, and then this vertical bar. So this means the set of all values of x such that, and then I give the rule for x. So in this case, what our set builder notation would be that all values of x such that x is not equal to 3 and x is not equal to negative 3. So let's go ahead and kind of highlight our set builder notation. I mean, we'll talk about it again later, but it goes along with domain. So back to the problem at hand. Now we have identified domain. So when we get done solving, if we find out, if we solve and get x equals 3 or x equals negative 3, we would have to throw that solution out because it's not valid. So back to solving. It looks like we have fractions. So we are going to need to clear the fractions. And do you remember how to do that? Remember, to clear the fractions, we are going to multiply each term by the LCD over 1. So we need to know what the LCD is. So from our first denominator, we have x plus 3 times x minus 3. The second denominator is x plus 3. I already have that in here, so I don't need it again. And the third denominator is the same. So that's what we're going to be using for our LCD. So I'm going to multiply each term by that LCD over 1. So I'll have x plus 3 times x minus 3 over 1. And I'm going to multiply that by my first term. And then plus the LCD over 1 times my second term, which was 4 over x plus 3, equals my LCD over 1 I'm running out of room a little bit. This happens to me a lot. Don't be surprised. X plus 3, x minus 3. Okay. Hopefully you can read that. Then we are going to simplify what we can. So as we multiply these fractions through, we would be taking x plus 3 times x minus 3 times x over x plus 3 times x minus 3. So the x plus 3's are going to cancel. The x minus 3's are going to cancel. And I will end up with x, well, these leave 1's in their place, so keep that in mind. X times 1, which is just x, over 1 times 1 times 1, which is just 1. So that leaves me with x plus. In the second one, the x plus 3's are going to cancel. And I'm going to have 1 times x minus 3 times 4. So I need to remember to distribute that 4 to both of those terms inside that parenthesis. So I'll have 4x minus 12 equals, and then here x plus 3 cancels, x minus 3 cancels, and I'm doing 1 times 1 times 3 over 1 times 1 times 1, which is just 3. So now our equation is a lot more simple. I am going to combine like terms here. So that's going to give me 5x minus 12 equals 3. Then I will go ahead and add that 12 over to both sides. So that leaves me 5x equals 15. Divide both sides by 5. And I get x equals 3. Now remember that we had those exclusions from our domain. So x equals 3 is not valid. X equals 3 was excluded by our domain. So we cross that out and we say that it is extraneous. If something is a solution that you found by solving, but it is restricted from the domain, then we call it extraneous. And that means that since that's the only solution we have, the answer to this equation, the solution to this equation, is that there is no solution. Okay, next example. -4 over x plus 4 equals -3 over x plus 6. Again, we have fractions, so we are going to multiply each term by the LCD over 1. The LCD in this case is going to be x plus 4 times x plus 6, because x plus 4 is like super glued together by addition, and x plus 6 is as well. So I would need to multiply by x plus 4 and x plus 6 over 1. Multiply this side by x plus 4 and x plus 6 over 1. Be careful when you have negative signs. So I'm going to show you that. We can cancel out the x plus 4's, and then we have x plus 6 times -4. It's not x plus 6 minus 4. We do need to distribute this -4 into that parenthesis. So we'll do -4 times x, -4x, -4 times 6, minus 24 equals. On the other side, x plus 6 is going to cancel. And I'm distributing -3. So I do -3 times x, -3x, -3 times 4, minus 12. And then we need to move stuff around so that we can solve this equation. Now, this is, player's choice on which direction you want to go. Some people prefer to always put their variables on the left and their numbers on the right. Some people prefer to always make their variables have a positive leading coefficient. I guess it's just up to you which way you want to go. I tend to not care which side my variables are on. So I will add those 4x to both sides, and that's going to give me positive 1x. And then when I add 12 to both sides, On the left-hand side, that gives me negative 12. So I get x equals negative 12. What did we forget to do in this problem? Does anyone remember what we need to do when we have variables in the denominator? We need to get those domain restrictions. So for the domain restrictions, we need to take x plus 4, make sure that never equals 0, and x plus 6, make sure that never equals 0. So that gives me x can't equal negative 4, and x can't equal negative 6. So if I needed to put that in set builder notation, that would be squiggly bar x such that x cannot equal negative 4 and negative 6. I think you can put them both in there. I don't think you have to write x cannot equal twice. I think you can do it like that, but don't quote me on that. Then we check this against our domain. We got x equals negative 12, which isn't restricted, so that's going to be our solution. Okay, on to literal equations. Literal equations, when you get done solving them, they're not going to have like x equals 7. They're going to have like all kinds of letters and numbers and weird stuff going on when you're finished. So when you're solving literal equations, you're going to be solving for one variable in terms of the others. So think about like when you're given the equation of a line and they ask you to put it in slope-intercept form, you still end up with x's and numbers. Y equals like 7x minus 4. It's kind of like that, except for these are a bit more complicated. So they're always going to tell you which thing you need to solve for. So in this case, they want us to solve for x. So I need to get this x by itself. Remember also, when you are solving equations, you're basically going to be doing order of operations in reverse. So I would want to start with my adding and subtracting to both sides and then move on to my multiplying and dividing. So the first thing I'm going to do is subtract this 1 from both sides. So subtract the 1 to get it away from my blob that has the x in it. Then I have, the 1's go away, negative ax equals c minus 1. Then I'm still trying to get this x by itself. So I will want to divide by negative a. Now you have two options when you do that. You can independently divide c by negative a and negative 1 by negative a, or you can divide the entire side by negative a. That's going to leave us with x equals c minus 1 over negative a. Now, math people are kind of weird. I mean, you all know that already, but we generally don't like to have a negative like that in the denominator. So without usually writing it down, what mathematicians will normally do is think about multiplying the numerator and the denominator both by negative 1, which is a legal move. I can multiply the numerator and denominator both by the same thing. And then that's going to give me x equals, so I've got to distribute negative 1 times c, negative 1 times negative 1, so negative c plus 1 over a. And that would be the most acceptable answer. You could write it 1 minus c over a if you wanted, but that looks pretty. Okay, let's throw something new in here. Find the number d for which x equals 2 is a solution of the equation x plus 2d equals x minus 4 plus 2 times d times x. So basically this is asking us to assume that x equals 2 and we need to solve for d. So this x is a 2, this x is a 2, this x is a 2. And then we need to solve for d. So basically solve for d when every x is a 2. So I will rewrite this as 2 plus 2d equals 2 minus 4 plus 2 times d times 2. So clean it up. 2 plus 2d equals, I think I'll go ahead, no, I'll leave it. 2 minus 4 plus, I'm going to multiply those together, 4d. Then if I combine these like terms here, 2 plus 2d equals negative 2 plus 4d. And then again, player's choice about which direction to go. I'm going to go ahead and subtract 2d over to that side, which is going to leave me 2d on the right. And that means I am adding 2 over to this side. So I get 4. Then, of course, divide both sides by 2. And I get d equals 2. Now, this one didn't have any domain restrictions. So we have indeed found the number d for which x equals 2. Okay. This guy. Solve for r. Yikes. So this little R1 and R2, those are what we call subscripts. And this is actually the formula for resistance in a series of, when you have a series of resistors, the overall resistance, 1 over the overall resistance is 1 over R1 plus 1 over R2. And you can keep going however many resistors you have in the series. This should remind you, hopefully, of the working together formula from Algebra 2, because it's exactly the same thing. These resistors are working together to give you the overall resistance. Anyway, we're going to solve for this R right here. I see fractions in this problem, and whenever I see fractions, I'm thinking I need to clear the denominators. So I am going to start off by clearing my denominators. This ultimately is the guy I'm trying to solve for. So I will multiply by the LCD over 1. The LCD is going to be R sub 1, R sub 2. So all those over 1. Multiply. Multiply by R sub 1, R sub 2, and R over 1. Multiply by R sub 1, and R sub 2 over 1. Because these are all different. The R's are different from each other. Then I'll go through and simplify what I can. So here I've got that R cancels with that R, leaving me 1s in their place. R sub 1 cancels with R sub 1. And R sub 2 cancels with R sub 2. Then when we multiply our fractions, remember we go straight across. So 1 times R1 times R2 times 1 will be R1, R2 over 1 equals R times R2 over 1 plus R1. Now we are trying to solve for this R here. Now this presents a unique problem that we haven't yet seen today, and that is that we have more than one term that has the variable we're trying to solve for. So we have a specific strategy for that. So this is when more than one term has our variable that we're trying to solve for. So the strategy when that happens is that we need to get all of those terms on the same side and everything else on the other side. Okay. So we already have that going for us. All of the terms that have the regular R are together on one side. The term that doesn't have the regular R is by itself. So the next thing we're going to do is factor out our variable, because it's like a GCF. So we're going to factor out, excuse the bells, that capital R. So that's going to leave the left side the same, R1, R2 equals, bring the R out to the front, which is going to leave us R2, because we put that out front, plus R1. And then we're just going to divide both sides by the parenthesis that we left. So then we'll divide both sides by R2 plus R1. And we get R1, R2 over R2 plus R1 equals R. Now I want to talk to you for a moment about what, if anything, could be simplified. I mean, I just boxed it, so you're probably assuming that nothing else can be simplified, and you would be right. When I see R2 plus R1 like that, I have to think of that like they are super glued together. Like if those were numbers, if R2 was actually a 2 and R1 was actually a 1, that would be a 3. Whereas this would be a 1 times a 2. So I can't separate that 3 because it's kind of grouped together in the denominator. So I cannot simplify the R2 with the R2 unless everything was multiplied. There will be more on that later through the semester. When in doubt, though, go ahead and ask me, can I cancel this or not? And here it is, domain. So this is going to be a page in your notes that you will want to bookmark for frequent referring as we go through the entire semester, because it's like knowledge that I'm expecting you to be responsible for owning. So like later on when I'm like, hey, what's the domain? And I ask you, what do we need to be worried about? You got to be able to recognize where domain restrictions come from. So I kind of want to start out by telling you that if there are no restrictions, then the domain is going to be all real numbers. So what is a restriction and how do they happen? Well, we've already talked about one type of restriction, and that's when we have what we call rationals that look like this. Those are the ones that have variables in the denominators. There go those bells again. There'll be another one in a couple minutes, like a minute. When you have variables in the denominator, you're going to find the restrictions. Do you remember? By setting the denominator not equal to 0. So that's actually going to tell us what the denominator doesn't include. Okay, so let's practice that here. I see that I have x squared minus 4 in my denominator. So I want to set my denominator, x squared minus 4 cannot equal 0. And then to be able to solve that inequality, I'm going to need to factor x squared minus 4. Remember that is difference of squares. So it's going to factor to x plus 2 times x minus 2, which of course means that x plus 2 cannot equal 0, or x cannot equal negative 2. X minus 2 cannot equal 0, or x cannot equal 2. If we're putting it in that set builder notation, the domain would be that curly brace x such that x cannot equal 2 and negative 2. But there's a couple of other ways that we can put that. One is to use what we call, well, I guess it's not called anything. It's on a number line. And then the other thing we're going to do is interval notation. And we will cover interval notation in a lot more detail in section 5. So I want to look at this on a number line. So on a number line, my domain is going to be all the numbers except negative 2 and 2. So if I exclude negative 2 and 2, then the domain is going to be all the rest of those numbers. In interval notation, we are going to read from left to right. So as I go left to right on this number line, the first important number is negative infinity. The next important number is -2. When I have a gap in my number line, in my shading, I have to stop and start up again, and I use the letter U. So then I go, important number is -2, next important number is 2. So -2, 2. I have another gap, and then 2, and the arrow is infinity. Every time I have an infinity, I'm going to close with a parenthesis. Every time I have an open circle, I'm also going to close with a parenthesis. So that would be my interval notation domain. There are 3 shaded regions, so there are 3 intervals. What's another domain restriction? Let's see. We have rationals, which have variables in the denominator. We have radicals with even indexes. So an even index is like 2, 4, 6, 8. Who do we appreciate? If there's an odd index, you're not going to have any domain restrictions. So we really, mostly, honestly, you're going to deal with square roots almost exclusively, but it also applies to like 4th roots and 6th roots. So when you have a radical with an even index, the restricted domain is where the radicand is greater than or equal to 0. So let's say I have a square root. The radicand is the stuff that's inside, and the radicand must either be positive or 0. So the way that we make that happen is we take the radicand and set it greater than or equal to 0 and solve. So here's my example. To find what my domain is, I am going to take the radicand only, that's this part, 4x plus 5, and say that has to be greater than or equal to 0. I would go through and solve my inequality like normal. And I find that x is greater than or equal to, there's my fraction, -5/4. Don't make that a decimal for me. Leave it the way that it is. So if I'm putting that in set builder notation, that would be the curly brace, x such that the rule is that x has to be greater than or equal to -5/4. On a number line, I'm going to have -5/4. X is greater than or equal to that, so that gives me a closed circle and everything to the right. And then in interval notation, again, we'll go over interval notation more in section 1.5, so don't panic too much if you're unsure about it. We're going to list 2 numbers. I only have 1 shaded section, so I have 1 interval. My first number is -5/4. My second number is that arrow, infinity. Remember that every infinity gets a parenthesis, and then a closed circle is going to get a square bracket. Then we sometimes have things that double up. So we want to watch out for those double dippers. Here's what I mean by that. This problem right here has 2 domain restrictions. One, it has an even index radical. So here's my radical. I have to make sure that 4x plus 5 is greater than or equal to 0. And the second thing is that I have a denominator. I have variables in the denominator. So when that happens, I need to set the denominator not equal to 0. So square root 4x plus 5 cannot equal 0. So when I put these two ideas together, like imagine I square both sides of this, then I would have 4x plus 5 cannot equal 0. But I also say 4x plus 5 has to be greater than or equal to 0. So it has to be greater than or equal to 0, but it can't equal 0. So when I put those two ideas together, that basically just tells me that 4x plus 5 has to be greater than 0, but not equal to. So how does that change my notation here? Basically, it's just going to take off the equal part. So set builder notation, the domain would be x such that x is greater than negative 5/4. How does it change my graph? In my graph, I'm going to have an open circle at negative 5/4 instead of a closed circle. And in interval notation, that is going to change from a closed circle, which is a bracket, to an open circle, which is a parenthesis. So those are my representations for domain. Now, back to the beginning, I had said if there are no restrictions, which right now means even index radical or variables in the denominator, if there are no restrictions, then your domain is going to be all real numbers. So we should write that down. If there are no restrictions, then the domain is all real numbers. In interval notation, we write that negative infinity to infinity. So when does that apply? Well, every time we have a polynomial. Polynomial functions never are going to have any restrictions. So we can go ahead and put that in the bank. I'm picking a color. That's what's holding me up. I know, I realize that's dumb, but it is what it is. So polynomials have no restrictions. So the domain for every polynomial is negative infinity to infinity, or all real numbers, or set builder notation, x such that x, this little symbol means is an element of, it's like a C with a, I don't know, it's like a curvy E. X is an element of the real numbers. Okay, what is next on our pages? Discounts and markups. I'm going to give you a formula to use for discounts and markups. And that is this guy right here. We're going to take the original price plus or minus the percent change as a decimal times the original price is going to equal the final price. So obviously we will be subtracting if we have a discount, adding if we have a markup. Do you remember y'all remember how to change a percent to a decimal? Let's just write it down. To change a percent to a decimal, you're going to move the decimal point 2 places to the right. And then obviously to change a decimal to a percent, we're going to move the decimal point 2 places to the left. So we've got a movie theater that marks its candy up 275%. Candy sells for $3. How much does the theater pay for its candy? So let's see what we know. Do we know the original price of the candy? Do we know the percent change? Do we know the final price? So it says a movie theater marks its candy up 275%. So that's going to be our percent change. But we need to change it to a decimal. So we take 275%. Remember, we're going to move the decimal point 2 places to the right to change a percent. Whoa. Yeah. Hopefully y'all caught that. To change a percent to a decimal, we move to the left. To change a decimal to a percent, we move to the right. My bad. So our decimal point is right here. We move it 2 places to the left. So our percent change as a decimal is going to be 2.75 because it's over 100%. That's why it's a number bigger than 1. Candy sells for $3. Is that the original price or the final price? Wants to know how much does the theater pay for its candy. So that's before the markup. So this is going to be the price after the markup. So this is going to be our final price because it's after the markup. And then how much does the theater pay for its candy? So that's going to be the original price. So X will be our original price. And then we go through our formula. The original price, which was X, plus or minus, well, they're marking it up, so it's plus. The percent change as a decimal, which is 2.75, times the original price, which is still X, equals the final price, which was $3. And now we're just going to solve this equation like we normally would solve any equation. X plus 2.75x, that's just a matter of combining like terms, because remember I have an invisible 1 out here. So 1 plus 2.75 would be 3.75x equals $3. And then divide both sides by 3.75. Now in this case, we are going to use a calculator because we're doing a story problem. We want to have a decimal equivalent answer. So hang on while I get my calculator. You guys might be using your calculator on your Chromebook. I'm using this guy. So we'll do $3 divided by 3.75. There we go. Equals 0.8. Now, since X is a price, money usually has 2 digits after the decimal point. So I'll go ahead and remember that there's a 0.80. So the original price that they pay is 80 cents for candy. And then they mark it up to $3. And that brings us to the end of 1.1.